minus 1 in constant time. And you can see that all I need to do is just do some shifting and addition, right? So to go from here to here, what I need to do is I need to shift all the digits to the left by 1 and then add the new digit, right? So you can see that that is, and shifting is nothing but multiplying by 10, right? So I need to multiply by 10 and then mask out some of the digits and then, or rather mask out the least, the most significant digit and then shift in the new, the new digit, right? So once I do that, so you can see that this particular operation can be done going from ti to ti minus 1 can be done in constant time. Therefore, the whole problem can be solved in time proportional to the length of t, right? Because you set up a window and then you move the window right by one position, and that requires constant time. Therefore, to shift it all the way through t is going to take you time proportional to n, right? So the specific operation that you need to do to get ti plus 1 is this, right? So you need to remove the most significant digit, right? The most significant digit is ti, right? Ti is the leftmost, right? Ti, ith position is here, I plus 1 is here, I plus 2 is here, right? So you want to get rid of the ith position, then you need to multiply, you need to take it out, and the nth position has an exponent of 10 to the power n minus 1, right? So if you look at the expression for defining lowercase p, that is the numeric value of corresponding to the string p, then that is given by this expression which says 10 to the power n minus 1 times p of 1, right? So if you want to take that digit out, then you basically have to subtract this quantity from your ti, okay? And so this is basically the notion of you want to take this out when you go from here to here, right? So that is the subtraction that's going on there. And then you want to add the new digit, I plus n. And so that is adding that digit, that is this operation. So you can see that ti plus 1 can be computed in from ti in constant time. Okay, so once we have done that, well, we have again another efficient algorithm, right? So from a complexity perspective, KMP algorithm and shift and algorithm, they are all they have the same complexity as this algorithm, right? So there's no difference, right? So of course, what's the problems? So we seem to have an algorithm of the right complexity. So what is the difficulty? What is the disadvantage of this algorithm, let's say, as compared to the shift and algorithm that we looked at last time? Word size. Well, shift and algorithm had a word size issue too, right? So it's not exactly shift word size. It is related to word size, but you need to be more specific if you compare it with the shift and algorithm that we discussed last time. So what is the assumption we need for the shift and algorithm? What needs to fit within a word?
The number, the number being compared, the pattern.
So we want the length of the pattern to be less than the number of bits in a word, right? That's what we need. So what do we need here? So in a sense, for each character in the shift and method, we are allocating 1 bit, right? So it's more like, whereas here we are probably spending more like a byte per character, right? Because, well, I showed you the case where everything is a number, but if you think of characters in English, for instance, right? Then of course you're going to need more or less a byte of storage for each digit, right? So in that case, well, you're probably talking about being able to handle only in relatively small patterns if this is exactly how you do it, right? If you do it then like this, then your patterns are limited to be of size, 4 or maybe 8, right? Whereas in the other case, you're probably you're dealing with patterns of length 32 to 64, right? So this is 32 to 64 seems like a reasonable number. 4 to 8 doesn't look like a reasonable number, right? So what can we do? So that brings us to this technique called Rabin-Karp fingerprinting, where we do exactly the same thing, except that because we cannot store a big number, right? So in this case, P was 4 digits, and we could store that in a single word. If it was 24 digits, well, we couldn't possibly store that in a single word. And so what could we do? One thing we could do is we could say, what happens on computers when you keep multiplying large numbers, right? You just lose out some bits and you retain the least significant bits, right? Or in other words, some kind of modulo operation goes on, modulo 2 to the power n, where n is the number of bits in your word, and so basically you keep the remainder, right? So we can do the same thing, right? We could say, well, we cannot store the exact value, but what if we store just the remainder when you take a modulo with respect to some number? Then what happens is that, well, you're not guaranteed when there is a match, you're not guaranteed that the two are equal, but the likelihood of match is relatively small, because if the base of the mod is large enough, let's say 2 to the power 32, then the probability of an accidental match is something like 1 in 2 to the power 32, right? So you are not likely to have accidental matches, and therefore it's okay to say, okay, I'm going to take the modulo, compare them, and if they compare out, if they check out, then what I'm going to do is I'm going to basically redo the match. Okay, I'm going to repeat the match from scratch because, well, I don't know for sure that there is a match, right? So this time I'm going to spend order of n time to verify the match, but it's okay if the probability of doing this full match is very small, then I'm happy to do it again, right? So that's the basic idea. So all you do is you take the same simple algorithm, and instead of trying to store the entire value of the corresponding to that window in a single number, you just store its remainder with respect to some prime number. Okay. So instead of working with n-digit numbers, we just say, okay, we are going to take a random prime, call it q, and we are going to store the remainder with respect to modulo q, right? And we know that modulo arithmetic kind of behaves very much like regular arithmetic, right? So we can do our multiplication and subtraction and all of those operations could all be done. We simply apply modulo at every stage, right? So that way we always have numbers which will fit into our word size. Okay? So q, the random prime q, is chosen so that it's going to be less than word size. Okay, and once you do that, then all the operations can be done in constant time, and now you have what would be called a probabilistic or randomized type of technique, and then you have all the benefits that you had before. Okay, with one small drawback, that the match is not guaranteed. If the numbers match, it still doesn't mean that the pattern matches. Okay, but again, the probability of a false match or a false positive, where there is a match based on the numeric value, but there is no match for the actual pattern, is basically like 1 by q, right? And if q is large enough, then the probability is very small, and since the probability is very small, you can it no longer really affects your perception of what the complexity is. So any questions? Yeah.
How do you slide it in both? Like, how do you get the
Okay, this is what we do, right? We take out the most significant digit by doing this, right? Because what is this? The multiplier for this digit is 10 to the power 3, right? Or 10 to the power n minus 1. So if you want to remove this digit out of this, then you have to subtract the most significant digit times 10 to the power n minus 1, right? So that is what we are doing here, okay? Modulo you can just apply afterwards, right? There's no problem in a modulo. That's what I'm saying. Modulo arithmetic works, and feels like regular arithmetic, so it doesn't really matter. You can just apply the modulo there, and everything else is fine. Right? You know the basic property of modular arithmetic, right? So you can do the same way. Of course, we apply one more mod q, right? But the point is that you can apply the mod at the beginning and then do the operation, or you can apply the mod at the end, and it doesn't really make a difference, right? So these are sort of standard properties of mod, and so we don't really have to confuse the picture by having to think about mod at the same time when we look at this expression, right? Because these are completely independent concepts. You can think of and understand this, and then simply say, I can just do mod on top of this, and it doesn't really, you don't have to go back and think everything, right? It's like saying, oh, I know, if I represent decimal numbers in a certain way, and I know how to add, and you also know that decimal numbers can be represented in binary form, and they can be added in that way. You don't have to understand every time, go back and say, okay, in order to really understand how addition works, I have to convert it into binary, right? You can say that's totally independent, the representation is totally independent of what is the meaning of the operation, right? And that's what I'm saying here. So the meaning is here, and the representation is sort of what the modulo thing is about. Okay, so this is how we take out the leading digit, and this is how we are bringing in the least significant digit. Okay, so you want to take this out, you subtract, multiply this by 10 to the power n minus 1 and subtract, and then you want to add this in, you simply add that because that's in the new number coming in is in the ones position, so you don't need any multiplier here, you just simply add. Okay, and in order to make this P and T fit inside a single computer word, you're simply going to apply this mod with respect to Q. Okay, and that's what is called Rabin-Karp fingerprinting, and it's called a fingerprint because it's a number, right? It's a number in some way summarizes the value of that substrate, right? Value of pattern P. And you can also see that you don't have to really work with numbers, right? You can work with any character, and all you need to do is, let's say you want to deal with characters that are 8 bits, then this will not be 10 to the power n minus 1, this will be 256 to the power n minus 1, right? Yeah?
So, why is it required for Q to be greater than X squared?
So Q has to be greater than, okay, so let's see, what is, so the point is that the number has to be large enough for you to reduce the probability of accidental match, right? And it has, this particular condition comes from, you make a probabilistic calculation of what is the expected runtime, and you want the expected runtime to be linear in n and m, okay? And in order for that to work, then the probability of false match should be something like 1 by n squared. Okay, otherwise the numbers won't add up. Okay, but intuitively you can understand that okay, Q should be large because you want to minimize the probability of the numbers, the remainders matching, but the strings not being the same. So you want Q to be as large as possible, right? And if you think about Q large greater than n squared, it's trivial, right? What we're talking about n is the length of the string, right? So length of the string, you might want to handle strings that are 100,000 characters. 100,000 square is still much smaller than what would fit into a word, right? So that's why it's not a big constraint.
But still, can we take the combination of the length of the string over the alphabet text? So that will give us more optimized.
Say it again?
Can we take the combination of the length of the string over
What do you mean permutation?
over the alphabet?
Why do you need to do a permutation? The order of characters matter, right?
Because that will give us the total number of space, right? The space in which like it will appropriate all the strings in that alphabet set over that length.
Okay, so you should think about it later and then talk to me, okay? Because some of the numbers you're talking about are astronomically large, right? Like number of possible permutations are so large that you can't really fit those things in anywhere. At least if I understand your question. Okay, so one of the issues is, well, okay, in order to prove these bounds, the algorithm relies on generating random prime numbers, okay? And generating random prime numbers is, it's not an easy task, So if you have to generate a random prime number, maybe that takes enough time that, you don't really gain a whole lot from this algorithm, because this particular task is not so efficient. So instead what we could do is we could instead use a random radix. Okay? So we are back to our interpretation of numbers as polynomials. Okay, again, remember, previously we talked about how the value of a number is given by a polynomial, right? So we said that so if you have this number 7521, right? That's equals 7 times 7x power n minus 1 plus 5x power n minus 2, or let me not say n. Okay, so let's just use numbers where x equals 10, right? So we said the way we understand numbers, we can understand them in terms of polynomials, and the way to convert an array of digits into an actual number is by applying this polynomial, right? Where the digits of the array are used as coefficients in the polynomial, right? So this is something we did in, early on in the course. And in this particular case, the example we looked at, we set x equal to 10. And then I also said, well, if you're talking about an arbitrary alphabet, then x would need to be set to the size of the alphabet, right? So if you use, say, an 8-bit alphabet, well, then your x there should be set to 256, okay? So what we could do is we could interpret this as a polynomial, right? Now, what I want you to think about is that for these if two patterns are equal, right, then the number that you compute here is going to be the same whether I set x equal to 2 or 5 or 10, right? If these coefficients are same, right, and I want to say I'm going to define let's say I define a function f that takes a pattern P, okay, and produces an integer, okay. Now I can apply that to another string q and it will give me another integers, okay. So let me say P and Q, okay. So what I'm doing is that if P and Q are equal, then I'm saying, okay, the capital P and capital Q are likely to be equal, okay. Now let me make the radix an explicit part of this, right? Okay, and let me call this P10 and Q10. Okay. Now I could also define some G in the same way. Now I use, let's say, 20 as the radix and produce P20 or the point is that if this P and this Q are equal, right, then it doesn't matter whether I use 10 here or 20 here, these two will be equal, right, because I'm just applying the function whatever it is, right. So the radix that I use is not going to matter, right. So in the sense that I'm going to, if the patterns themselves, the strings themselves are the same, then it doesn't matter what base I use, I'll still get the numbers I compute to be the same. Okay, which says that I am not constrained to use a particular radix such as sigma. I can use anything. Okay, and still my argument, roughly holds that if the numbers match, then I have a high probability that the strings themselves match. Okay, so that's what is being done here. I'm going to use, instead of using generating random primes and what I'm going to do is I'm going to fix a prime. Instead, I'm going to use a random value for x. Okay. So why are we using random values? What is the purpose of using random values? So why did we use random values in quicksort? Random pivot in quicksort? Because otherwise there can be pathological cases where there is where the list splits in a bad way and you get a quadratic time algorithm, right? And you want to force expected n log n time. Well, the only way you can force it is by making it random. Okay. The same way here, if you think through and work out the details, you can always construct cases where there are strings such that you can have false matches all the time. And so you want to make sure that those pathological cases don't arise, and one way to force those pathological cases out is by making sure that that your input is random. Okay. So in fact, the next chapter we are going to next set of algorithms we are going to talk about are randomized algorithms, and so we'll naturally get to that point. But here, the basic idea is, again, you want to make sure that these pathological cases don't arise. Okay, and that's why we keep talking about random. Okay, so again, the difference between this Carter-Rabin-Karp algorithm and the original Rabin-Karp algorithm is that we are making something else random, right? Instead of working with a random prime number, we fix a prime number, so this way you don't have to generate some random prime number each time. All you need to do is to generate a random base, which is simply a random number, right? So that's much easier. We know how to generate random numbers, and then everything else works. Okay, and in fact, if you work through the details, what you'll realize is that, okay, we are talking about polynomials, and we are talking about the case where there is where the numbers match, okay, and then we want to ask, okay, if the numbers match, what is the likelihood that the patterns themselves would match? Okay, this can be very easily posed as a question where the polynomial p is equal to the polynomial ti, okay, and then you can ask how many possible values of x for which this can happen, okay, and that is simply a question of asking what are the roots to this polynomial, right? So p of x minus ti of x equal to 0, how many roots are there? Well, if you are working with, we know that if you are working over the field of real numbers, an nth degree polynomial has n minus 1 roots, right? So it turns out that if you are working with polynomials not over a real field but a field defined by arithmetic modulo a prime number, the same property holds. So you can have only n minus 1 roots, which means that n minus 1 by q of the q possible choices of x will result in a false match. Okay, so you can see that your q greater than n square, right? You see this over here, because if q is greater than n square, then this will become less than 1 by n, right? And therefore the probability of false match will be small, right? You can imagine that, okay, you want the probability of false match to be, say, 1 by n or less, and that's where that comes from. Okay, so I want to this type of hash is called a rolling hash, right? So fingerprint, we call it fingerprint, we call it rolling hash. They are sort of the same thing, and the main point here, why the word rolling hash is a little bit more specific than a fingerprint, and it tells you that you can incrementally compute it as you slide your window to the right or left, right? So that's why the word rolling comes. So as you move this around, then you can very quickly calculate what is the new hash. Okay, and this is the same expression we looked at before, except that previously x had a specific value of 10. Now we are saying, okay, x can be any value. Okay. Now if you look at how long does it take to compute this, right? Once again, this is the computation of ti plus 1 from ti. We want to do this in order 1 time, right? So you can see that even though you have your multiplication by x to the power n minus 1, right? So computing x to the power n looks like order of n time, but it is a fixed value, right? So once you choose x to the power n minus 1 can be computed once for all, and you're done, right? So this is already computed even before you start doing anything. And so all you're left with is one multiplication of p of I by this quantity, right? And then another multiplication by x, and then some additions, right? So you have a couple of multiplications, and so that is obviously order of 1, and not only order of 1, actually a small number of operations. So the shifting or sliding operation is actually quite efficient, okay? And but there might be scenarios where even this, 2 multiplications and additions, you might think is too much, and you might say, I need something that's even faster, okay? And how can you do that? Well, if your exponents are, if x is chosen to be a power of 2, well, then you can avoid multiplication and use shifts, right? But then, of course, it's no longer random, and that's the trade-off. Okay, so you can make it more efficient, but then you might lose some of the properties that you otherwise have. Okay, so I'm going to talk about specifically about this function called Adler32, which is a very widely used rolling hash. Okay, in particular, it is used in your gzip and in particular, and also in zlib. Okay, zlib is basically a library implementation of the functionality of gzip, and pretty much anything that's transmitted on the internet, is often compressed without even your knowledge. Somehow, somewhere, some compression is going on, and it is using this zlib, and that is in turn using this function called Adler32. You really don't have to see what. There's nothing to really understand, right? There's some arithmetic going on. All that matters to you is, okay, you are computing modulo 65521. Well, 65521 is kind of close to 65536, and that makes it easier to do some of the modulo arithmetic faster. And so you can see that all that I want you to take away from here is that the operations here involve only addition. Okay? And there is no multiplication or division involved. Okay? Because although you are computing the mod here, this is addition, which means that all you will do is you'll add, and then you will check whether it has become larger than this. If it has, then you will subtract. Right? So there's no need to do any division to do the mod here. Okay? The same thing over here. You can again say do this in an efficient way. And as a result, you can compute this function without using either multiplication or division. Okay? So I won't go into this particular thing. Instead, I will jump to talk about where these rolling hashes are used. As I said, gzip uses this. Okay? So you might remember this question from your first midterm. Why does it take a long time for gzip to compress? Right? So why does it take a long time? Because it has to look up the strings in the current window and then say, okay, did this string occur in the previous window? Okay, so it could have appeared anywhere in the previous window. So it has to have an efficient way of finding if this substring, okay, is appearing in the previous window. And remember, this substring that I'm talking about, we don't have a length in place, right? We want to say, what is the longest substring here that has appeared before, right? So one way we can do this is by maintaining a hash table. Right? We compute these fingerprints, right? Adler fingerprints, and you put them in a hash table. And then what you do is you compute this rolling checksum in the current window. As long as there is a match, you keep extending it and extending it. And when there's no longer a match, then you say, okay, meaning when I say no longer a match, it means the hash doesn't appear in the hash table. Right? The fingerprint doesn't appear in the hash table. So at that point you say, okay, I just have the longest string that occurred before, and then I pick that up. Okay. So again, I don't necessarily, I'm not necessarily expecting you to go back and write down the gzip algorithm based on the description, but the idea is to just get a rough idea that you are using this type of fingerprinting to figure out whether the string has occurred before. Okay? And even though it is using this efficient algorithm, still it takes time. Okay? Because of a number of factors. One of them is, of course, entering and looking up things in hash table are still somewhat expensive. And secondly, because the number of strings in hash table are so large, the possibility of false matches and so on are also relatively high, and as a result, in spite of the fact that you're using efficient algorithms, still gzip is not very fast. Okay, so rsync is another algorithm that relies on these types of hashes. Okay, rsync is a very nice program that you can use for synchronizing data across the network, okay, and so you will see that if you're using Linux or some other Unix version, you will see this program explicitly. You will see it, But if you use other systems, let's say Dropbox or something else, underneath they are using the same set of techniques to try to reduce the amount of data that is exchanged between the two copies, right? So you have some copy of the data on your laptop and you want to sync it with something on the network, and you want to make sure that this can be done fast, right? So you might have gigabytes of data that you share. Obviously you don't want to send all of the gigabytes over the network in order to figure out whether everything matches up. So you need to do something much more efficient, and rsync is really the workhorse behind all of that. So what it does, well, the naive approach for doing this is to say, okay, let me just do a diff, and then whatever is the difference, only that I will transmit. But unfortunately, to do a diff, the data needs to be in one place, right? So you can say, well, I can reduce the data that I need to transmit once I transmit all the data once, right? So that's not very meaningful. So you need a way of comparing the data while sending only small amounts of data over the network, right? So this is yet another use of the fingerprints, right? This has nothing to do with the efficiency of the algorithm itself, but it has everything to do with the amount of data that you can transmit on the network, right? So by using these fingerprints, you can say, I'm going to send a small fingerprint over the network, and if the fingerprint matches, then I'm going to say, okay, with a high probability, the files match. Okay. So what it does is actually it uses the rsync uses this approach in there are sort of three tests that it does. Right. One is it does a timestamp check. Okay. So if the size of the file and the timestamp match, then it says, okay, it's probably the same file. It probably hasn't changed. So then it doesn't try to do anything more. Okay. The next test it attempts is to compute an Adler checksum. Okay. So you compute the Adler checksum and then see whether that matches. And if it matches, well, then there's a very high likelihood that the two files are same. But that's not enough because there is still a non-zero probability that they may not match, right? And it will be tragic, it will be catastrophic if you say, okay, the file is there, but in fact, the copy of file is not there, right? So you need to be really sure. So what it does is that if the Adler sum matches, then it uses the MD5, right? MD5 is a cryptographic hash function, and the probability of false matches on MD5 are extremely small, right? So you think of probabilities in the range of 1 in 2 to the power 128, right? And that probability is small enough, right? So the probability of you being struck by lightning is so much higher, or there being a cosmic ray coming into your computer and frying it. Those are all in the range of probably 1 in 2 to the power 30 or 40, right? So it's 2 to the power 128 is just it's a very large number or a very, very small problem, so you don't worry about it. Okay. So once MD5 matches, then it just declares that the files actually match. Okay. Now again, obviously you can't do any better because the only way to be really 100% sure is to actually send the data over, right? Which defeats the purpose. So the best you can do is to say I'm going to use something like MD5, and if it matches, I'm going to say, the file is the same. So whatever I said so far works if the only thing you're interested in is checking if the entire file is identical, right? But when is the last time that's enough, right? That certainly helps if you are only changing a few files, but most of the time what happens is that you make small changes to your file, right? So you want to make sure that these small changes require only transfer of small amounts of data, not the copy of the entire file. Okay. So what it does is instead of computing a fingerprint on the entire file, what it does is it constructs windows of length 128, right? So what it does is that it takes the file, breaks up the file into 128 byte windows, and then what it does is it basically takes the fingerprint for the first 128 bytes, sends it over to the other side. The second 128 bytes sends it over to the other side. Okay? So, let's say you have your file and you've broken it up into 128 byte, right? So, and then what rsync does is it transmits a checksum for each of them, right? So for 128 bytes, if you use ADDL 32, then you are sending 32 bits, right? 4 bytes for 128 bytes. So that's a relatively small amount of data, right? So, but the problem on the other side is this. Okay? So it's possible that there was, all that you did was inserted a character at the beginning of the file. Okay? If you did that, then here is a file on the network, the 128 byte block on the network. It looks like this, whereas here the same information is like this, right? Because you inserted a byte, right? So if you calculated the checksum for the first 128 bytes and sent it over there, okay, unfortunately there isn't a match exactly at the boundary, right? So there is a shift error, right? So what happens is on the server side, what the algorithm is doing is actually it is computing not this kind of checksum, but a rolling checksum. So it's going to compute checksum for this 128 bytes 1 through 127 or 128, and then it's going to compute the checksum for bytes 2 through 129 and 3 through 130 and so on, right? So on the server side, you're computing all the possible checksums. So here, you're computing n by 128 checksum, right? And here, you're computing n minus 128 because that's the number, if you do this, slide a 128 byte window through n, the number of distinct blocks will be n minus 128. So what it does is that these n by 128 checksums are compared with each of these, okay? And notice that as far as the data that needs to be transmitted, I only need to transmit n by 128, right? But on the other side, the number of comparisons I'm making is of the order of n, right? But the data that I'm transmitting has been reduced by a large factor, okay? In particular, I have reduced it by a factor of 32, right? And but still, I can tolerate things like shift errors and still figure out, okay, that this file is has only small changes, and I can send the diff, okay? And whenever you talk about binary diff, right? Doing a diff on binary files, this is basically what goes on, right? So you use some sort of a rolling hash, and then you compute on one file you compute these checksums with fixed size blocks, and on this side you slide this fixed thing so that you get to compare not only the corresponding blocks but also all the blocks that are shifted by 1, 2, 3, whatever number of bytes. Okay, so you shift by arbitrary number of bytes, you will still be able to get it. Okay, so that's what is done on binary diff. So we are not using, they don't use edit distance on binary files. What is done is this kind of block-based diff, which is using this kind of rolling checksums. Okay, so that's how this problem is solved. Any questions?